my short answer is no. And so I thought it would be good to get a panel of people together to offer perspectives of what can be done and what needs to be done on a variety of issues right now in ocean acidification. So today we're going to hear from scientists what science needs to be done. We're going to hear about what other drivers of ocean acidification there are, local drivers that need to be addressed in the current regulatory framework that exists to address them. We're going to hear about coalition building and getting different interest groups involved in ocean acidification. And lastly, a perspective on public perception and understanding of ocean acidification and potential tips for messaging. So what I'm going to do is I'll introduce the speakers now. They'll each speak for about 10 or 15 minutes, and then we'll have a question and answer. I'll have a few questions, but I'll invite you all to have questions as well. Now, the first speaker is Dwight Gledhill. He's an oceanographer with NOAA. He works at the Atlantic Oceanographic and Meteorological Lab in Miami, Florida, and also has a connection to the University of Miami. He researches ocean acidification monitoring, mainly the geochemistry, but also potentially vulnerable ecosystems like coral reefs. And that's what he'll talk about today. Actually, Dwight's going to take a little bit longer because he's going to explain the basics, the ABCs of ocean acidification, and the current state of knowledge, and then explain what NOAA's plan is, the overarching plan to address ocean acidification in this country. Then we'll hear from Foley, who is a research fellow at the Center of Ocean Solutions at Stanford University. And she's going to talk about recent research that will come out soon with a group of colleagues on local drivers of ocean acidification and the existing regulatory framework to address those drivers. Then we'll hear from Brad Warren. Brad Warren manages the Productive Ocean Partnership Program, and he was the founder and director of the National Fishery Conservation Center. Brad's going to talk about his work to connect with fishermen and to establish a coalition of interested people interested in ocean acidification from the fishing community. And then lastly, we'll hear from Lisa Dropkin. Lisa is here in rare form since she threw her back out this morning. I'm very appreciative that I lost my cell phone, which couldn't cancel. She's a principal at Edge Research Center, which is a marketing research firm. But before that, she worked at SeaWeb as a research director. And she knows a lot about people's attitudes and values towards the ocean. She recently completed research on people's understanding and perception of ocean acidification. And she's the one that's going to give us some clues on how we might message around that. So, our first speaker, Dwight.
Grab this.
I'm not sure how you can get that computer.
No, that's fine. This should work like this, I believe. Yes, it does. Okay. Is there any way we can dim the front one? Or probably not? Anyway, hi. Perfect. Okay. So, I've been given the rather unpleasant task of delivering you the basic geochemistry of ocean acidification. So I'm going to start with that. We're going to start at the top level, and we're going to work ourselves through chemistry. And just before you want to gouge your eyes out, I will then switch to the ecological implications of it. Okay? And then I will talk a little bit about where NOAA is in terms of our strategic planning, where we intend to go, and what our priorities might be related to ocean acidification. So we're going to start at the absolute top level. As a geochemist, we are intimately interested in the cycling of carbon amongst the planet. Okay? And the largest reservoir of all carbon on the planet is obviously in the geological reservoirs. And we try to quantify the flux of how much carbon comes out of the geological reservoir and goes elsewhere. Right now, our best estimates suggest that as a consequence of fossil fuel burning and cement production, somewhere on the order of close to 8 gigatons of carbon is emitted from the geological reservoir, okay, into the atmosphere. We find, however, that not all of that carbon resides in the atmosphere. Only about 4 gigatons of carbon per year annually are increasing in the atmosphere. That's a whole other issue. Where does the remainder of that carbon go? Much of it is absorbed by trees, grasses on the land, which we diminish by the fact that we cut many of those trees down, we burn them, kick that back out into the atmosphere. But the net deficit, the difference between all those numbers, is somewhere in the order of about 2.5 gigatons of carbon per year is being taken up by the world's ocean. So ocean acidification specifically pertains to that 2 gigatons of carbon that finds itself up into the surface ocean. We can define it as representing the direct chemical change to global ocean chemistry in response to rising levels of atmospheric carbon dioxide, and it is in addition and really apart from any possible effects that CO2 might have on the climate system. So, this is where you start gouging your eyes out, but it's not that. I won't go far. If you take carbon dioxide, a gas, and you dissolve it in water, any water, a glass of water, it will form carbonic acid, okay? Which is this species over here, this that will form, right? Which, because it's an acid, rapidly dissociates and forms a hydrogen ion. And when we talk about pH, and the scale of pH, it's really a measure of the concentration of hydrogen in the solution, okay? And so as you generate hydrogen, it actually causes a depression in pH because it's on a funny scale. It's a log inverse scale. So as you add hydrogen, pH declines. Hence the term ocean acidification. The oceans are not going into battery acid. That isn't the case. In fact, they're going to remain rather alkaline, okay, for quite some time. But we talk about ocean acidification because it is literally that act of generating carbonic acid into the ocean. So this happens in a glass of water. It's basic fundamental chemistry. It should happen in the oceans. And we can now, by virtue of our long-term time series stations, actually monitor the changes that are occurring in the ocean. This is the NOAA observatory in Dwight, which you're all familiar with. And we see increases in atmospheric PCO2. And just as you'd expect in a glass of water, surface ocean pH is in fact declining again. Chemically unusual about that. People have known about this for several decades now, and it didn't actually get a lot of media attention up until perhaps the last decade or so, when there seems to be some indications that there is ecological sensitivity to these changes. Most of the research has focused around organisms within the oceans that produce shell materials out of calcium carbonate, which you might know as chalk. Okay, it's actually several mineral phases of it, but it's all calcium carbonate. And they run everything from corals to lobsters to many aquatic organisms at the base of the food chain. And the reason that it's a concern is because if you take a look at this hydrogen ion, which is the generated, okay, it's now free within seawater to react with other species within seawater. And one of those species is this guy here, who I am not a fond of, is the carbonate ion, okay? And by reacting with the carbonate ion, you form more bicarbonate. Well, chalk, calcium carbonate, as you can see in the equation right here, is partly composed of carbonate. So, through the uptake of CO2, and the formation of carbonic acid, you actually take up and consume carbonate ion. So the availability of carbonate ion for the production of calcium carbonate mineral phases, either through inorganic means, through precipitation, or through biologic means, through calcification, becomes less available. All right. This is where you definitely got your eyes out, perhaps, but fear not. I'm going to talk a lot about, the remainder of this talk about this Greek term, omega. Okay? And all omega does is it defines, it's just a simple ratio. It's not that complicated. It just looks at how supersaturated seawater is with respect to carbonate mineral phases. Okay? When omega takes on a value greater than 1, it's favorable thermodynamically for the precipitation of solid phase minerals. If omega goes less than 1, it means dissolution sets in. Okay? It's no longer thermodynamically favorable. So you've got a snowball that you build in the wintertime, you move it into the summer months under the beach of Miami. It is no longer thermodynamically favorable for it to persist there. Okay? That's what happens when omega shifts less than 1. So, simple thermodynamics. If we increase CO2, as we've seen over the industrial period, there should be declines in pH, there should be a corresponding decline in carbon ion, and saturation state will lower. And if we project out over business as usual scenarios, the change is rather significant. Okay? That's just the basic fact. So, for decades now, we've been actually trying to quantify and inventory the amount of carbon in the ocean. This is a series of cruises. This is international inventory of cruises that occurred back in the 1990s, cataloging the carbon in the ocean. In fact, they've actually been able to parse out isotopically specific amounts of carbon which are found from anthropogenic sources. Okay, fossil fuel. And from that, we can start generating maps of saturation state in the world's ocean. And what you'll find from this map, 2 points. One thing to note is all the waters, almost all the waters, barring a few exceptions, which I'll talk about, are supersaturated with respect to aragonite, the primary mineral phase of a lot of marine organisms. Okay? That's a good thing. That means if you're generating a shell of calcium carbonate, it's going to stick around. It's not going to dissolve in surface waters. Okay? You don't find a lot of cases where we fall below a value of 1. Okay? We have now started to monitor the changes in saturation state by using a combination of ship and buoy observations, which we synthesize with satellite observations. This is a product that I work on, which tracks the changes in saturation state within this greater Caribbean region. That's Florida, Cuba, Puerto Rico. Okay, so over the past 20 years, we see this significant seasonality in saturation state, largely driven by temperature changes, which also influences saturation state. But you see this secular decline associated with the uptake of CO2. But an important point to make here is all the values are still considerably supersaturated with respect to those mineral phases. Precipitation, calcification is still thermodynamically favorable. Right? We can also take a look closer in at the local effects on a reef system, which we're doing now. We've got buoys deployed in Puerto Rico, and we find that as a result of local biogeochemical processes, perhaps Melissa will talk more about this, local effects, that you can actually generate CO2 on a reef. Okay? So reefs tend to be sources of CO2, albeit very small globally. But locally, they are a source of CO2. And the result of this is they actually depress saturation states even further than what we see regionally. So you may look at the maps of saturation state in the ocean. There's actually a step down as you move on to the reef. Furthermore, other processes which act locally and regionally, which can change saturation state, stuff like coastal upwelling. A recent cruise that happened in 2007, where they ran transects along the west coast of the United States and Mexico, actually mapped out periods where, as a result of upwelling, CO2-rich subsurface water is actually pushed up onto the coast. And as a result, you can actually have periods of actual undersaturation, where carbon minerals are thermodynamically favorable to dissolve. You actually get dissolution. This is where Dick really works about corrosive waters. Okay? And in some cases, so these are episodic events, and in some cases, many of the economically significant resources of our nation are located in areas where these episodic events can occur. So, this is a secondary process which is overlaying on top of this global effect of ocean acidification. Dick Foley calculates that the acidity, I don't really like that term, but the degree of saturation state is actually substantially lower as a consequence of the uptake of anthropogenic CO2 within these waters. So while naturally these waters would be at lower saturation state, the concern is that they are actually stepped down a little bit further in saturation state levels as a consequence of the uptake of CO2. Okay. So we can then start to ask ourselves, well, what did saturation state look like in the pre-industrial period? And here's a map. This is, I think, Dick Foley and James Orr developed this map, mapped out estimates of what saturation state levels would be. We know what atmospheric concentrations were in the pre-industrial period. And what you find is, similar to what we saw in the other figure, everywhere things are supersaturated. Tropical waters where coral reefs reside, which are where all these little dots are in waters which are saturated at least 4 times supersaturated with respect to aragonite. high latitude systems are perhaps twice saturated with respect to uranium. Our concern is if we're looking at a business as usual scenario in terms of atmospheric CO2 emissions, we get out to about the year 2100, we actually see much of the high latitude regions actually going undersaturated. Okay, so dissolution will occur. It has to. It's basic thermodynamics. Okay, you may be an organism that can actually produce calcium carbonate under these conditions, but you won't persist. You can't. Right? You will note, however, that coral reef carbonate mineral precipitates is in part a function of the degree of saturation state. We now find, through a number of recent experiments, that the rate at which many marine organisms calcify follows very similar kinetics. So as you dial down saturation state, you in fact dial down the rate at which many marine organisms can calcify. So even though coral reefs will remain for the foreseeable future in waters that are supersaturated with respect to uranium, the concern is that their rate of calcification will decline, and this is before you take on the effect that I showed earlier, where there's a step down in saturation state to move on to the reef. Okay? So, just a sampling. It is not comprehensive. How am I doing on time? Oh, wait. How long do you have?
You started late, but I think you should get
a minute or two. Okay. Very quickly. So there have been a number of experiments out there now. Many of them are inconsistent with the preliminary findings. It's a very complicated set of experiments coming out right now, but there have been a number of indications that at least some species of Coccolithopores, if not all, are sensitive to changes in saturation state even before you actually undergo dissolution. So there's a number of marine organisms that show sensitivities. Perhaps some of the more economically significant ones, at least immediately, might be stuff to look at mussels and oysters, which all show declines in the rate at which they calcify under higher CO2 levels, probably attributed to changes in saturation state. Some recent experiment looking at bivalve juveniles of these hard shell clams, where we put them in sediments which are undersaturated, shows that mortality is significant under these conditions. It may naturally be so. In many cases, this is a natural amount of mortality of these organisms. However, the concern is that if saturation states decline globally, that the mortality rates would increase. Okay. Coral reefs, as I've indicated, will remain supersaturated, but a couple things to consider. Coral reefs, the persistence of a coral reef is a balance of processes. The coral reef has to calcify enough material every year to make up for other natural losses as a result of mechanical erosion, storms, which export material off the reef, bioerosion, parrotfish picking away at it, actual dissolution that can occur within the sediments. A coral reef, if it's maintained, has to calcify enough to at least balance these losses. There seems to be some indications that we've seen declines in coral calcification rates from some studies in the GBR, but these are, I would say, inconclusive at this point, so whether you can attribute it specifically to oceanification. We have experimental evidence that crustose coralline algae, which help to bind the reefs together, is significantly effective at higher CO2 levels. We can look at natural systems which occur now, which are exposed by upwelling zones, like I showed earlier, where saturation states are quite low. And we find that in those systems, those reefs have very little cementation binding the reefs together, and the bioerosion rates are through the roof. This seems consistent with experimental evidence that shows that bioerosion rates increase as a result of higher CO2 and lower saturation. What might be the economic impacts of ocean acidification? It's probably very early to get hard figures on this. Sarah Cooley, Dropkin, Suatoni did a recent study, and they found that all the organisms shown here in red and yellow are potentially directly susceptible to ocean acidification. Okay, they account for perhaps 2 billion in terms of primary commercial sales. In addition to that, organisms which predate on these other species may be secondarily impacted by ocean acidity. Potential impacts of ocean acidification range everywhere from the calcifications I talked about. There are chemical changes in nutrient and trace element speciations, shift in phytoplankton diversity, reduced growth potential for lifespans of adults and juveniles and larvae, which is a really heavy area of research right now, is that different life stages can have different susceptibilities. Okay, very quickly. Okay, I'm back. Here's the NOAA National Plan. All right, am I on time? I'm close. Okay, so as a consequence of all this that we know and we don't know, NOAA has set out to develop a coherent strategy in what its priority areas of research are that seem to fit within its mission purview. And we've recently compiled this NOAA Ocean and Great Lakes Acidification Research Plan. Okay? This is in part in response to recent legislation, the FOARM Act, Federal Ocean Acidification Research and Monitoring Act, which mandates that NOAA work towards developing a comprehensive interagency strategy to monitor and conduct research, looking at specific organism responses to ocean acidification, establish a research and monitoring plan, and establish a program within NOAA for assessment and consideration of regional and national ecosystems and socioeconomic impacts. This program will literally start and be staffed tomorrow. No, Monday. Okay? So, our priority areas, obviously, monitoring the trends in ocean acidification, both in the oceanic environment and coastal zones, looking at really the ecosystem responses, which demand us to look at species-specific and multi-species effects. We want to model, in a geochemical sense, what these effects might be as we project out into the future. Develop adaptation strategies, if not for the organisms, at least for the human communities that are dependent on the species that might be impacted. And then, of course, to try to educate and outreach as best we can. Oftentimes, maybe not sending the geochemists to do talks. But, so there are three primary hypotheses that we are trying to answer, at least with our monitoring and research aspects, which is one, looking to see if the rates and the magnitude of ocean acidification will actually vary in different areas. We know this will be the case. We're trying to at least validate that. We're testing this hypothesis. Will, in fact, ecosystems be changing structure and function as a consequence for that? What might be the adaptation potentials of those organisms and those ecosystems? And we also anticipate, and it seems like much of the new research is showing, that there's a heterogeneity in species responses, okay, that we need to know and understand to quantify what the total ecological impacts might be. So in terms of a regional approach, which is how we've developed the plan, we've got the Northeast region, Southeast, West Coast, Pacific, mostly the remote islands, and Alaska. Right now, today, what's going on in the Alaska Fisheries Science Center is they are investigating the specific impacts on king crab, canna crab, polyp, and larvae. The Northwest Fisheries Science Center, they're looking at Pacific oyster impacts, the Olympia oyster, geoduck, and pinto abalone. The Pacific Islands Fisheries Science Center is engaged in conducting surveys in the remote islands of what their carbonate chemistry is, and together with academic partners such as Woods Hole, actually quantifying the rates of coral calcification. We're doing monitoring studies for calcareous algae effects. Northeast Fisheries Science Center is looking at phytoplankton and fin fish larvae. Southeast Fisheries Science Center is now engaged in coral reef species, and specifically they're doing some very interesting work at looking at some of the early stages of coral and the effects that it might have. Pacific Marine Environmental Laboratory, well, that's got Dick Feely, enough said. So he's engaged in ocean and ship mooring observations and geochemical modeling. He is the Analytical Center, Washington Pacific, NOAA, and counterpart where I work at AWOML. We are also an Analytical Center, and I specifically work a lot with satellite applications and the effects on coral reefs and monitoring ocean acidification in coral reef environments. So, concluding remarks, ocean acidification, it's a global scale change in ocean chemistry, although there are local effects, especially in coastal zones, which have to be very carefully considered. And these changes represent probably the most rapid shift that we've seen in a million years in ocean carbonate chemistry. So, at a minimum, they're enough to take notice. High latitude systems will likely experience undersaturation with respect to radonite within the century. Most, but not all, species-specific response experiments demonstrated negative effect of ocean acidification, even before dissolution And the precise ecological implications remain uncertain, and considerable research needs do remain. And the socioeconomic impacts, I dare say, are less so understood. So an observational network is definitely needed, and we're trying to advance that within NOAA right now, including within coral reef zones. Physiological response studies, some of them have begun already within NOAA. Mitigation and adaptation studies, again, maybe for the organisms, maybe for the communities that depend on the impact of organisms, needs to be developed and integrated with models, and geochemical modeling studies that include ecological impacts all need to be advanced and should be done so. How close was I?
Not too bad.
Not too bad.
You got it. I'll give you more time. So
Okay.
we'll go on to Melissa.
Hi, my name is Melissa Foley. I'm with the Center for Ocean Solutions at Stanford University. So when we talk about ocean acidification, there's getting to be more attention paid to this by scientists as well as industry media. But often we're still talking about the usual suspects of atmospheric CO2. And these include things like coal-fired power plants, vehicle emissions, as well as deforestation. And we know that carbon dioxide in the atmosphere has increased 40% since pre-industrial times. About 30% of anthropogenic CO2 has been absorbed by the oceans. And with that, we've seen a resulting 0.1 pH unit decline throughout the oceans since pre-industrial times. And again, while a 0.1 decline doesn't seem like that much, as Dwight mentioned, the pH scale, like the Richter scale, is logarithmic. So a 0.1 change in pH translates to roughly a 25% increase in hydrogen ions in the ocean. And so we know that ocean acidification is happening. We know that it's because of increasing levels of atmospheric CO2. But we're also finding that these decreases in pH across the ocean basins are not the same, that there's a mosaic effect occurring, and that there's ocean acidification hotspots that are growing. And we're finding that many of these are occurring in coastal waters, those glacier shore population centers. And this is important to consider. Approximately 25% of primary productivity is occurring in these nearshore waters, and about 50% of world populations live in these coastal communities. So today, we're going to sort of bring to light some of these additional causes of ocean acidification and what may be driving some of these coastal acidification hotspots. So some of these examples include point source pollution of nutrients and pollutants, erosion and runoff that's caused by things like deforestation in non-urban areas or coastal development, atmospheric as well as runoff of fertilizers from agricultural areas, as well as NOx and SOx emissions from industrial sources. And then finally, also upwelled water, as Dwight mentioned, that's bringing these corrosive waters to coastal systems, which is by and large a natural process. But we're becoming more aware of this low pH water that's coming into shelf areas. And the thing to consider about each of these drivers here that we're starting to understand a little bit more about is that each of these can have detrimental effects to the ecosystem by themselves, but also in combination in the total of those, as well as with the other combination of stressors that are occurring in coastal ecosystems, including overfishing, habitat destruction, and increasing sea surface temperatures. We don't completely understand how all of these are interacting in these systems. And these impacts can have very local ecological impacts, so impacts to oyster reefs, growth of corals, as well as prey species for iconic species such as salmon. And these drivers can also have severe economic impacts on these coastal communities, including seafood production, tourism, from things such as diving, as was talked about this morning, as well as revenues from fishing. So if there are local drivers and there are very local impacts, this sort of creates a perfect storm where local and state agencies can start to act to address some of these stressors. And in the absence of international and national climate policies that address atmospheric CO2, we can start to discuss the avenues that are available to local, state, and regional governments to start to address some of these drivers that are also contributing to ocean acidification. So just to run through some examples here, for point source pollution, the Clean Water Act directs state agencies to ensure that discharge and runoff of pollutants is monitored, limited, and consistent with the functioning of aquatic ecosystems. And a recent lawsuit from the Center of Biological Diversity against Washington State essentially sued the EPA for saying Washington State has failed to list their waters as impaired due to changes in pH. And the EPA went through a process of comment and review of their policy for listing pH and has now sort of given the green light essentially to states to go ahead and focus on pH and to list hunting species such as salmon. And these drivers can also have severe economic impacts on these coastal communities, including seafood production, tourism, from things such as diving, as was talked about this morning, as well as revenues from fishing. So if there are local drivers and there are very local impacts, this sort of creates a perfect storm where local and state agencies can start to act to address some of these stressors. And in the absence of international and national climate policies that address atmospheric CO2, we can start to discuss the avenues that are available to local, state, and regional governments to start to address some of these drivers that are also contributing to ocean acidification. So just to run through some examples here, for point source pollution, the Clean Water Act directs state agencies to ensure that discharge and runoff of pollutants is monitored, limited, and consistent with the functioning of aquatic ecosystems. And a recent lawsuit from the Center of Biological Diversity against Washington State essentially sued the EPA for saying Washington State has failed to list their waters as impaired due to changes in pH. And the EPA went through a process of comment and review of their policy for listing pH and has now sort of given the green light essentially to states to go ahead and focus on pH and to list their waters as impaired when those pH levels go outside of that range, of the normal range of variability. So for erosion and runoff, there are the Coastal Zone Management Act is an example of where land use policies can be used to address the issues of erosion and runoff. And the Coastal Zone Management Act just encourages states to preserve, protect, develop, restore, and enhance natural coastal resources, including the fish and wildlife that use these habitats. So focusing both on that development side, but also on what are the impacts to wildlife in those ecosystems. And through the Coastal Zone Management programs that states develop, they can declare pH as a factor in maintaining the quality of coastal habitats. And then in addition, local coastal development plans can also be used to address coastal erosion and where development is occurring in the coastal zone. In terms of these fertilizer emissions, there are many local land use laws and policies that can be used to address both coastal and riparian buffers that will reduce the amount of pollutants that are reaching the coastal ocean, as well as restoration efforts. And these can also be used to set limits on pollutants, and the Clean Water Act can be used to set levels on these pollutants that cause increases in pH in the coastal ocean. And then for NOx and SOx, the obvious sort of actions with the Clean Air Act, where this gives where enforcement of existing limits of NOx and SOx can be used, And the reason why we focus here on NOx and SOx and local drivers is because those have a much shorter residence time in the atmosphere, and so often they're deposited very close to the source. And so enforcing the limits that are already in the Clean Air Act can be used to tackle those issues. So this very sort of 30,000-foot level walkthrough of these local drivers and some of the local solutions that can be used are just to illustrate that it is in the best interest of local, state, and regional authorities to act now in the absence of these national and international agreements to reduce atmospheric CO2, and that the sooner that they start to address these issues, potentially the better off these ocean acidification issues will be in the coastal ocean. So just in summary, ocean acidification hotspots are developing, we know this, and we're starting to find that these hotspots are developing mainly in coastal systems. And really atmospheric CO2 is dominating the conversation, but that's only really part of the story here. There are local sources of water and air pollution that contribute to decreasing pH in coastal waters, whether that's through direct impacts of weak acids entering the system, such as from fertilizers or NOx and SOx, or whether it's these indirect effects of nutrients coming into the system and increasing productivity and ultimately decreasing the pH of the system. And that there are existing laws that can equip local and regional jurisdictions with tools to address ocean acidification now, rather than waiting for these larger scale efforts.
We're going to switch the order a little and have Lisa Dropkin go next so she can really go. Are you okay?
I just couldn't sit anymore.
This is
For those of you who missed it, I totally did something to my back this morning. Just like on the floor before I came here. But I'm propped up through a Motrin cocktail. Feeling better. Okay, so thank you, Brad, for letting me hopscotch. I think I've got some data that sets up what Brad's going to talk about pretty nicely.